I've discussed this topic before, but some nice new article came out in the Washington Post. Yes, Washington Post. Some of these reporters, Sarah Kaplan, I'm a big fan. There are other weather people who do an amazing job as well. And when they put together a story on science for the people, they actually do a very good job of explaining the main points. Once I start reading scientific papers, we always get technical. So I have fallen in love with reading newspaper articles to inform you, because many of my subscribers are also not climate scientists. They are from ecology, other fields where they need the science in a simplified form without losing the essence or the salient points and the critical aspects of why things are important that we are talking about and so on. So AMOC collapse, Atlantic Meridional Overturning Circulation, which you can look up on my other podcasts. There is water sinking in some places and then eventually it rises, and we know this happens. It circulates around the world and comes back to the places where it's sinking, just to keep the continuity of circulation. We call it the global thermohaline circulation. Within the Atlantic, we call it Atlantic meridional overturning circulation, because water sinks around the Greenland, Iceland, Norwegian seas, in the Labrador seas. Sinking water goes south, and then warmer, saltier water comes north, or at least it is saltier than other regions, and so on. And there have been some papers claiming that this is slowing down and this is imminently going to collapse, and so on. And one silly headline, even some headlines started shouting, I think last year, saying it may collapse as soon as 2025. Here we are in January 2025, just starting. And is there any chance that this will collapse? Pretty much zero, even though you'd never want to say never, but really we should be careful. And secondly, even if it collapses, exactly what will it mean in your backyard? We are not supremely confident about saying that, but it's not good news. So there is a risk, let's say, because Greenland glaciers are melting and the melting is accelerating. So these are all important issues. But the other thing is, what can we do about it, even if the predictions are accurate that it will collapse, let's say in 2080, 2100, whatever? What can we do about it? It still comes back to doing the things we should be doing: mitigation and adaptation. There is plenty of motivation to do those things. So do we want to add uncertain information? There is a scientific debate which is legitimate, but when you make false alarms, then it can do more damage than good. Okay, so we'll read this article, which nicely synthesizes the various papers and ideas, and then I will read one paper just very briefly to show how uncertain it is to use the current state-of-the-art models to estimate the time of collapse of this Atlantic meridional overturning circulation. Okay, so let's start with Sarah's article here in in Washington Post, that appeared on December 30th, so just a few days ago as I'm recording this. The oldest animal, well, I will be posting this much later because I'm way behind on posting. The oldest animal ever found could reveal whether a crucial ocean current will collapse. She's talking about clams. So clamshells could help scientists understand the Atlantic Ocean's sensitive circulation system and predict when that crucial system might catastrophically collapse. So these clams can live for a long time, provide a nice long time series, and they are, mid-Atlantic ridge and so on. They are at critical places where they can track these things. And I have another podcast discussing that the Florida current has remained stable for the last 40 years, which contradicts many of the other studies saying the Atlantic meridional overturning circulation is already slowing down. So you have an upstream branch that brings warmer waters to the sinking places that we mentioned. So comes across the equator, subtropics, into the Greenland, Iceland, Norwegian seas, and Labrador Sea. Labrador Sea has a slightly different process, but nonetheless you have an downstream process where the water is further making its way into the Arctic, and we have discussed the Atlanticization of the Arctic as well. Keeping all those background things in mind, let's see what Sarah has put together here. An assortment of Arctic clamshells at the University of Exeter Penryn campus in Cornwall, England. So that's a figure that I couldn't print. I can copy it and put it here, but anyway, clams were used in a study of the AMOC system. So sorry about missing the figure. It's just a prop of a figure. There was nothing image of clams. There was nothing outwardly impressive about the clams sitting on the deck of the research vessel Barney, Bjarni, Bjarni Samundsen. Okay, it's probably a Norwegian word. The dull grey creature dredged from the muddy bottom of the North Atlantic was no different from the billions of mollusks caught and cooked each year for chowder, little things, but this clam was destined for something greater than a soup pot. Okay, so some clams that live for a long time grow very big. These are not the ones that live for a long time, but if you get many of them over time, as you can from the sediments, then you can build a time series, which is the paleoproxies that we have discussed elsewhere. The humble bivalve, nicknamed Hafrun in Icelandic word meaning ocean mystery, was the longest living individual ever found by the scientists. For 507 years it bathed in the shifting currents off the coast of Iceland, watching the surrounding water become more or less salty, enduring the rise and fall of ocean temperatures. And as the years passed, it recorded those observations in the molecular makeup of its shell, tracking the trajectory of a changing planet from a spot no human could reach. Basically, they are synthesizing calcium carbonate, and depending on the temperature, there is a crystal structure, molecular makeup in the shell that can be used to infer past temperature anomalies, not total temperatures, but how temperatures were warmer or colder than a baseline, which is typically how temperature proxies or paleoproxies work. We call them proxies because they are not directly measuring temperatures, but they are giving us a proxy for a temperature change. Okay, so this one lives 507 years. There are some that live, I think, a couple of thousand years and so on. Once it had been viewed beneath a microscope, Hafrun the clam would turn into a historian, giving researchers new insight into the mysteries of the deep sea. It would serve as a benchmark, allowing experts to make sense of changes they see in the ocean today, and it would become an oracle, helping scientists predict whether human-caused warming has pushed the Atlantic's sensitive circulation system toward a tipping point that could devastate the modern world. So here, some journalistic liberties. When we say devastate the modern world, I'm not sure we have clearly evidence for that, linking AMOC to devastating the modern world and so on, but bad things will happen. And people have talked about past changes. The last one we have a good signal of is the Younger Dryas just before the Holocene started, where there was melting glaciers, sudden release of fresh water onto the North Atlantic, which altered the meridional overturning enough to get us back into freezing as we were coming out of the last ice age. And there is another little hiccup around 8,200 years ago, and so on and so forth. So it's obviously a sensitive circulation. Now we are saying it will collapse. So you have to be careful about what we mean by it collapsing. There is a circulation that is purely related to the fact that Earth is rotating in the ocean. Because it has boundaries, you get strong currents on the western side, and what we mean by collapsing is basically whether it will bring much less heat and not really change, because as long as the Earth is rotating, we are going to have a western boundary current, but what it brings and how it affects the sinking will of course be affected. So the amount of heat moved will be affected. The circulation will in many ways change because of the sinking changes and so on. So many details. Experts have long known that the Atlantic Meridional Overturning Circulation, or AMOC, the system of ocean currents that transports heat and salt between the southern and northern hemispheres, can suddenly and irreversibly shut down as a result of rising temperatures. A growing number of computer simulations, including 2 preliminary analyses published this summer, have suggested a collapse could occur as soon as 2050. There is a lot of debate about this, and it's highly unlikely. IPCC says in this century up to 2100 it's very unlikely that this will happen, but of course these results came after the synthesis of the last IPCC report. Yet many researchers warn that those findings can't be confirmed without the real world data, and scientists haven't been monitoring the AMOC long enough to detect trends in its behavior or determine exactly when it might change. So remember that. Enter the clams. The ocean history these organisms record provides a natural laboratory to really understand the system, said David Reynolds, a marine climate scientist in the University of Exeter. We can answer questions we couldn't ask before. Okay, so you are only not only asking newer questions, but you are also able to answer them. And reading a newspaper article is that a good thing about it is that we also get some comments from scientists when we do podcasts from papers. We are not doing that style, right? So what's the Earth's circulatory system? Just to give a brief introduction, scientists often refer to the AMOC as a conveyor belt of the ocean, carrying waters across the hemisphere from the surface to the ocean depths, but that metaphor belies, I don't know how you pronounce it, belies the sheer size and complexity of the current, which is more akin to human circulatory system. It's a core component of a healthy planet, as vital as blood, as powerful as a beating heart. That's a journalistic explanation, but basically the waters that sink in a few places go to the bottom of the ocean at various depths. They go around the world all the way into the North Pacific and back, and in the Southern Ocean, and mixing happens. Waters come back. We know why that happens, but we don't know where the energy for converting that water back happens, and so on. But this can take hundreds of years, and you have to remember those time scales. So this is obviously very important, because when waters sink, they take greenhouse gases with them, they take heat with them, and they take oxygen with them. And we have obviously a perpetual reminder that oceans are taking up over 90% of the additional energy we are producing by increasing greenhouse gases. So this circulation is a very critical part of that. The cycle starts in the South Atlantic, where the surface of the ocean is warmed by the tropical sun. As the water drifts across the equator and starts moving northward, it begins to evaporate, concentrating salt in the current that's left behind. Basically, there is water flowing from, let's say, near the southern tip of Africa and moving across the equator, evaporating, getting saltier, and getting to the bottom of the Greenland region. And there a lot of evaporation happens, and when evaporation happens, salt remains, which makes the water heavier, and that can sink, right? The cycle starts in the South Atlantic, as we said. That warm, salty water is propelled through the Caribbean, past the East Coast, and across the Atlantic toward Europe, where it runs into the frigid waters of the Arctic. Laden with salt and starting to cool, it becomes denser and sinks towards the bottom of the ocean. This deep water then travels south along the seafloor, getting warmer and fresher and less dense, until it finally hits Antarctica and is pulled back to the surface. A little bit of a simplification, but it doesn't matter. I've discussed conveyors, the great conveyor belt elsewhere, global conveyor belt elsewhere. So if you want more scientific details, you can follow up there. The world as we know now, it's a product of this vast overturning. The AMOC moves carbon deep into the ocean and transfers heat at a rate of 1 quadrillion watts per second, 50 times the rate of energy used by humankind every year, I think. It shapes the band of clouds that encircles the Earth at the equator, delivering rain to Africa, the Amazon, and brings balmy temperatures to northern Europe, explaining why Scotland is much milder than Alaska, and Newfoundland, despite sharing the same latitude. So time scales are being mixed. When we talk about clouds at the equator, we're talking about longer time scale of where the rain band is, the so-called intertropical convergence zone. But when we talk about milder temperatures on European side versus the North American side, we are talking about faster time scales, multiple years, and so on. But as a climatology, Europe is milder now as well, right? The differences in temperature and salinity are the engine of AMOC. As long as the North Atlantic water is salty enough and therefore heavy enough to sink as it cools, the system is self-reinforcing, so you have this nice virtuous cycle going on. Yet over the past century, humans have warmed the planet by more than a degree Celsius, 1.8 degrees Fahrenheit, and caused the Greenland ice sheet to melt at a pace now exceeding 270 billion tons of ice per year. That influx of fresh water interrupts the salty northbound current, slowing its descent toward the seafloor. Well, there is some debate about what are all the processes involved in making this happen. After reminding ourselves that maybe the slowdown itself is a debated issue, but there's no doubt at all that Greenland glaciers are melting, and the melting is getting faster, and that meltwater is flowing on to critical regions of where the deep water forms. If meltwater continues to flood the North Atlantic, many experts fear the AMOC may cross a tipping point at which it can no longer sustain itself, abruptly and irreversibly shutting down. This is where all the debate starts, because when it will happen, how much fresh water it will need, and so on, there is no real control. Okay, a study published this February in journal Science Advances used the amount of fresh water moving around the South Atlantic to suggest the AMOC had gotten much weaker. Some of the same researchers suggested in preliminary analyses this summer that the system is likely to collapse around the middle of the century if the world remains on its current warming trajectory, and that it could tip even if humanity manages to limit warming to just over 2 degrees Celsius. So this is where a lot of the reliance on models comes in, and the next paper I will read talks about just how uncertain these things are in models and where the uncertainties come from. So take it all, take all this in with a pinch of salt. Appropriate metaphor, adage, right? Meanwhile, real-world observations have revealed subtle signs that the system isn't functioning as it should, even as the rest of the planet warms as a result of the greenhouse gas emissions. A patch of water below Greenland has gotten colder, a hint that the ocean conveyor belt isn't carrying as much warm water as it once did. But there are other debates as well, that more circulation changes are happening to the north of where the water is forming and not to the south. So we have to be careful. This is how science works, right? There are uncertainties, but we are seeing some things and we're trying to understand why that's happening. And we still don't understand fully. And we have to be careful that we don't understand and what potential consequences could be, right? So, in October, dozens of top climate scientists issued an open letter calling on Nordic leaders to take seriously the risk of an AMOC collapse in the coming decades. Even a partial shutdown could lead to dangerously harsh winters in northern Europe, as well as sea level rise on the east coast of the United States and dramatic shifts in rainfall around the equator. All true. If you see in a movie called The Day After Tomorrow, you will see this scenario play out, but I won't go into the detail here. Yet ongoing uncertainty about AMOC's future makes it hard to communicate the threat, scientists say. So what can you actually do about it, even if you did communicate the threat successfully? That's a very big question, right? Computer simulations may suggest a collapse is possible, said Maya Benyami, a climate scientist at the Potsdam Institute for Climate Impact Research, but they don't perfectly simulate the complexity of the real world. So Potsdam and then Tim Lenton, whose name will come up, are very vocal about this imminent collapse. Okay, she found that the model, she found that the models used to predict AMOC's behavior are too full of uncertainties to pinpoint exactly when the system could collapse. So I will read the abstract and a few details from her paper. And direct measurements of the current strength gathered by a network of floating sensors only go back 2 decades, not nearly long enough to detect significant change in a system that takes 1,000 years to complete a single cycle. So are we pushing this too much by saying it's about to collapse? If you want to do some sort of extrapolation into the future, you need something that goes back much further in the past than Yami said. This is really A very important point to remember, because when people start shouting loudly about something that is so uncertain, we have to be aware of what the potential consequences could be in terms of the response or lack of response. Because what if some dictator decides that, oh, AMOC is collapsing, so I'm going to take control of your life and do things this way because that's the only way to survive. And this can happen, right? The trees of the sea, sclerochronologists, scientists who tell time through shells and bones, sclerochronologists, I don't know exactly how it's pronounced, can't take credit for discovering that clams are astute record keepers. That honor goes to Aristotle, who in the 4th century BC observed that lines on the animal shells represented a year's worth of growth. Imagine, he noticed it. But it wasn't until the last few decades that researchers realized they could use those lines to learn about the history of the ocean, much the way they use tree rings to understand past temperatures and weather on land. Wide line in a shell generally indicates a year of warmer waters and abundant food, Reynolds explained. The types of carbon and oxygen atoms found in the lines can point to whether clams' habitat was dominated by deep Arctic water or warm surface currents from the south. Few species are more valuable for this research than Arctica islandica, the group of bivalves that includes hafrun as well as many of the other clams eaten by humans. In the frigid waters of the North Atlantic, where creatures grow old by growing slow, cold waters, slow growth, metabolism slow, you live long and so on. They are Antarctica islandica that were alive to see the invention of thermometer, the founding of New York, and the discovery that sun sits at the center of the solar system, Copernicus and so on. So again, artistic rendering of science. No other organism has been tracking the oceans in precise detail for as long, not even humans. That's how they got the nickname of as the trees of the sea, Reynolds said. Okay, I have to track my phone calls because I have a reporter coming soon. Yeah. Okay. ETA 11. Okay, I have also a visitor coming. So okay. Where was I? Trees of. Okay, but it wasn't until the last few decades that we figured out how to do this, and they're called the trees of the sea for that reason, just like tree rings on land. Nearly 2 decades ago, a young researcher, Reynolds, was hired to help sort through thousands of living and dead clams that had been collected by the RV Bjarni Semundsen in a laboratory at Bangor University in Wales. He painstakingly sliced the shells open and peered at them under a microscope, looking for patterns and seeking out overlaps in their rings. Measuring down to a fraction of a millimeter, he drilled microscopic samples from each annual line and determined their chemical compositions. By matching up the shells from clams of different ages, Reynolds and his colleagues were able to create a timeline that extended 1,357 years all the way to the middle of the 7th century. That's when the last blip occurred. The chronology published in 2016 remains the longest annual record from anywhere in the ocean, Reynolds said. Other kinds of evidence, such as layers on seafloor, extend further back in time, but they can't be pinpointed to specific years, making them less useful for cause and effect analysis. In other words, when you have these paleoproxies, you have to worry about what is the time resolution of the information you are getting. If you're getting some point of information for every year, it's tremendously useful. Okay, whereas sediments and other things blur the timelines because they're accumulating and getting disturbed, and they're storing information, but only 10-year level information, sometimes 100-year level information. So they can go far back, but the resolution in time keeps dropping, where this is very useful to have annual band for 1,357 years. Okay, you have to have absolutely dated material to diagnose what's happening and what's changing first, said Iowa State University geologist Alan Wanamaker, who also worked on the clam timeline. For the first time, we could say, did this cause this to happen, or did it respond because that already happened? Crucially, the clam data came from a spot on the border between the AMOC and the Arctic waters, where the ocean conditions are heavily dependent on the strength of the currents flowing from the south, and the chronology encompassed a dramatic climatic shift, the transition from the relatively warm ocean conditions of the medieval period to a much cooler 500-year stretch known as the Little Ice Age. That's going back in time. Little Ice Age came in the 15th, 16th, 17th century, just before the Industrial Revolution began. They got attention of Beatrice Arellano Nava, a fellow researcher at the University of Exeter who specialized in climate tipping points. She was on the hunt for subtle changes in AMOC's behavior that might indicate it was on the precipice of critical slowdown, she said. Okay, so maybe I will break the podcast into two pieces, because this is about 25 minutes and we have a bit more left to read. Especially if I just read the article, it takes about 10-11 minutes, but since I'm adding commentary that's essential for translating this to you with some science added, it's going to take longer, but that's okay. So we have the clam story now, then we bring somebody who's going to interpret the time series with the information we have on what we are looking for in terms of what climate did that got recorded in the clams, right? So we'll come back and read, and maybe we'll finish in the second podcast. Okay, see you soon.